Anytime we send information from one computer to another, whether that's over the internet or even a simple wired connection like this, there's a lot involved to make sure that the information is received correctly. Depending on the network or connections involved, there are lots of different ways for errors to occur. And often the reliability of a network depends more on detecting and correcting these errors than avoiding them altogether. So over the next couple videos, we'll look at some mathematical tricks that we can use to detect and even correct errors. And I'll show you how some of that math can be done really elegantly in hardware with just a handful of logic gates. But before we get into any of that, in this video, I want to figure out the bare minimum of what it takes to send data from one computer to another. And for computer, I'm going to use these Arduino Nanos. So what's the most basic thing we can do to transmit information from one of these Arduinos and receive it correctly on the other? Well, if we're going to program one of these as a transmitter that's going to send some data, and we'll program the other as a receiver, let's start by figuring out how the transmitter is going to work. Well, one of the simplest ways to send data is with one data line that has two levels. If it's low, that means we're sending a 0, and if it's high, that means we're sending a 1. This is a pretty basic method, and this has a fancy name. It's called NRZ encoding, which is non-return to 0, which maybe sounds like kind of a weird name because it looks like it's going between 0 and 1 here. So what is this non-return to 0 business? Well, maybe the name makes more sense if you look at return to 0 encoding, which looks like this. So there's some baseline voltage level here, and then to send a 0, it pulses in the negative direction, and then to send a 1, it pulses in the positive direction. And then between each bit, it returns to 0. So that's what this return to 0 business is all about. But this is a bit more complicated, right? Because there's 3 different voltage levels. So we're starting to get outside the world of digital sort of on or off logic. So we'll stick with the NRZ encoding, where logic low means 0 and high means 1. So let's hook the first Arduino up and get it to transmit some data. So I'll connect it to a breadboard here, and I'll hook the 5-volt pins and the ground pin up to the power rails of the breadboard. And then for NRZ data, we just need a single data signal that we can control to go high or low like this. And so we can use any of the digital pins on the Arduino here. So I'll hook up an LED so we can just monitor whichever data pin we're using. And I'll hook this LED up to one of these data pins. And let's see, I think it's like D3 maybe. So our LED's hooked up to data pin D3 on the Arduino. And then I'll just hook the other end of the LED to ground with a current limiting resistor. I think this is 330 ohms, but anything that's a couple hundred ohms ought to be fine. And so now we ought to be able to transmit data by switching pin D3 high and low to transmit a 1 or a 0. And then we should be able to see that by just looking at the LED to see if it's on or off. And then at least give us a starting place to start to see what it looks like to transmit some data. So let's program this Arduino to transmit some data. So I'll start with the pin assignments, and we're just using pin 3. So I'll call pin 3 the transmit data. And we'll set that as an output pin since we're transmitting. Then of course we'll need a string telling us what message we want to transmit. So go with an old classic, hello world. And we're going to transmit one character at a time. So to keep track of what character we're on, let's loop from 0 through the length of our message, 1 byte at a time. Then the actual byte of data to transmit is going to be the character from our message at the current byte index. So each time through this loop, transmit byte will be one character from our message. But we can treat this character variable like it's an 8-bit number that represents the letter, since that's actually what it is. So then to transmit each byte, we'll need another loop to go through each of the 8 bits. So in here, we want to figure out if the particular bit we're transmitting is on or off. So to do that, we'll take the byte that we're transmitting and then AND it with a number that has 1 bit set to see if the same bit is set in the byte we're sending. So if we AND with 80 hex, that lets us test if the first bit is set, but we can then shift that to the right to test the other bits. So if bit index is 0, which it'll be at the beginning of the loop, then this is shifting right to the 0 places, which is not shifting it at all. And then we'll test the first bit. But then when we come through this loop the second time, we're testing, instead of bit 0, we're testing bit 1. Then it'll shift this bit that's set in this 0x80. It'll shift that 1 bit to the right. And then when we AND it with TX byte, we'll be testing the next bit. And then each time through the loop, we'll just be testing each bit on down the line through all 8 bits. So at this point, now we're looping through our message. So we're going one byte at a time through the message, and then for each byte, we're going 1 bit at a time through that byte. And then TX bit will be, at this point in our code, TX bit will be whatever bit we want to send. So now we just need to transmit that bit. And to do that, all we need to do is set the transmit data signal high or low, depending on the value of the bit we're sending. And that's pretty much it. So this will set the value of the TX data signal. That's that pin 3 that we hooked up to the LED. That'll set that high or low based on whether the transmit bit is is a 1 or a 0. So this will go through our whole message and transmit our whole message a bit at a time. But unless we add some delays, it's going to transmit it so fast we won't be able to see it do anything. And also, if we don't know how long each bit takes, it's going to be hard for the receiver to know how many bits it's getting. So let's slow it down a bit. So to make it easy to adjust, I'll define a target transmit rate here in bits per second. And just to start out relatively slow, we'll start with 5 bits per second. And then we can use this transmit rate of 5 bits per second to add a delay right after we output the new data bit. So we'll do delay, and then transmit rate is bits per second. So 1,000 divided by transmit rate will be milliseconds per bit. And so in this case, since transmit rate is 5, so 5 bits per second, this will give us, 1,000 divided by 5 will be 200 milliseconds. So in other words, we're going to have a delay of 200 milliseconds between each bit that we output. And if you think about it, the receiver is going to need to know this transmit rate in order to have any hope of interpreting this signal. But at this point, let's give it a try. So I'll go ahead and connect the computer here to the Arduino with the USB cable, and it's powered up. So let me just make sure I'm on the right port and go ahead and upload this. And it's done, and right away you can see the LED is blinking. So maybe that means it's signaling each bit. I don't know. It's kind of hard to tell if it's actually working right. It does seem to be outputting something, sort of randomish looking, but it's hard to keep track of what it's doing if you can't kind of look at it, 5 times per second and see exactly what state it's in, which is pretty hard to do just by looking at it. Although it looks like it's done sending the message and it's just stuck on. At least I'm assuming that's what's happening is that the last bit was a 1. But one thing we can do to check if this is working right, we could slow it down, maybe slow it down so it's sending 1 bit every 5 seconds, and then that would give us more time to actually consult a stopwatch or something and watch it. But that's kind of a pain. So what I'm going to do is I'm going to hook it up to an oscilloscope that will actually graph the voltage over time and give us a way to quickly see exactly what it's doing. And so now if we look at the scope, what we see that our voltage is up here at 5 volts. So 0 is here in the middle, and then it's 2 volts per division. So 2 volts, 4 volts, and this is almost 5 volts here. And so it's just constantly here at 5 volts. And that makes sense, right? Because our LED is on, so we're outputting a high voltage here. So we're seeing 5 volts here. And then the way I've got this set up now is each of these divisions across is 500 milliseconds. So two squares across is going to be 1 second. And then I can also do a single shot here that will stop it, and then it'll start once it sees a transition. So now if I reset the Arduino so it reruns that program and then outputs that data again, we'll reset it, and then we see it starting to output the data, and we'll see on the scope that it's going high and low. So we can actually see exactly what the LED was doing. So if we take a closer look at this, we can try to figure out if the right data is being sent. Now, since each horizontal division here is 500 milliseconds, that means this is 1 second. Now, since what we think we're doing is sending 5 bits per second, well, then we ought to be able to interpret this 1 second interval as 5 bits. So it looks like we've got 10010 here. So let's see if that matches what we expect. And we're sending the message hello world, so the first letter we're sending is a capital H. So if we take a look at an ASCII table, it looks like a capital H is encoded as 72 in decimal, or 1001000 in binary. And sure enough, that's what we see. Though we're sending each character as 8 bits, and this is only 7 bits, so presumably we need to include an extra 0 here at the beginning. And so now this is the first byte of our message. Now one thing to notice here is that it's not all that clear how to know where our message starts. I made a video a few years ago about framing that talks about solving that particular problem, but for now we'll just assume that we know how to find where that first bit is. So if this is the first byte of our message, then the next byte will just be the next 8 bits. So that looks like 0110, 0101, which represents a lowercase e. Then the next byte looks like 0110, 1100, which represents a lowercase l. So it sure looks like it's starting to spell out hello world. So it's great that we're able to verify that everything's working with the scope, but if you don't have a scope, or certainly as we start to make this thing a little bit more complex and want to keep troubleshooting it, it's going to be kind of a pain to have to hook that back up and interpret the bits just from looking at the graph there. So what I'm going to do instead is hook this LCD panel up to the Arduino, and then what we can do is update this LCD screen to show exactly what data we're sending and what we're doing, so it'll be a little bit easier to tell what's going on. And the way this LCD works, pretty easy to interface with the Arduino. There's a bunch of pins that you can connect here, but if you're not doing anything fancy with the LCD, which we're not planning to do, we just need to connect pins D4, D5, D6, and D7, just 4 of the data pins. And then there's the RS pin, the register select pin, and the enable pin. I think those are the only 6 pins that we need to connect to the Arduino. And then there's a few other things we need to hook up, power and things, but we'll go through all that. So I'll start by disconnecting the USB here. So, and then pin D4 on the LCD. I'll just hook up to D4, data pin 4 on the Arduino. And I'll do the same thing for D5. Just hook up D5 to pin 5 on the Arduino, hook up pin 6 to pin 6 on the Arduino, and hook up pin 7 to pin 7 on the Arduino. So those are the 4 data pins, just D4, 5, 6, and 7 that we need to hook up. Then we also need to hook up this RS pin, which is register select. And so I'll just hook that up to pin 8 on the Arduino. It doesn't really matter which pins, as long as we're hooking these up to some digital pins. In the code, we'll tell the LCD which pins it's using. And then finally, the enable pin we need to hook that up as well. So I'll just hook that up to pin D10 on the Arduino. So those are the only connections we'll need to the Arduino. But of course, we also need to give power to the LCD. So the VSS pin goes to ground and the VDD pin goes to 5 volts. And then, because we're not using the full functionality of the LCD, we're only going to be writing to it. We aren't reading from it. It has some internal memory and stuff that we're not going to use. There's this read-write pin. So if we just tie that to ground, the RW pin, tie that to ground, that just means we're always going to be writing to it. To do that, we only need 4 of the data lines. And then there's this pin V0, which is used for setting the contrast. And typically what you do with that is just hook it up to a variable resistor. I have this little potentiometer that actually came with the LCD. The LCD comes with a potentiometer, at least where I got it. So I'll just hook through the potentiometer to ground, and then we can adjust that to adjust the contrast. And then finally, there's this A and K, which are the anode and cathode of the backlight LED. And so we want to hook power up to that. So I'll hook the cathode of that backlight LED to ground. And then the anode we want to hook up to 5 volts, but of course we need a current limiting resistor. So I'll hook that up there. And I think that's a 330 ohm current limiting resistor, but anything, a couple hundred ohms ought to be fine. And so there we go. So hook this back up. We see the backlight comes on. And of course we're sending our data, but nothing's going to display on the screen because we haven't written any code to use it. But let's go and take a look at that. And for the LCD, we're just going to use a library that does most of the work. So if you go to Sketch, Include Library, Manage Libraries, I just want to make sure there's this liquid crystal library and make sure that's installed. So we've got that. And then we just go up to the top and we'll include that. And then I'll define the pins that we're using. So we've got LCD, D4 through D7 are the data pins. And then LCD RS is the register select, and we hook that to pin 8 of the Arduino. And then the LCD enable pin, we hook to pin 9 of the Arduino. And so basically, before we do our transmit loop here, I'll just initialize the LCD. And so you just define this object, and then in the constructor, we're going to send in all of the pins that it uses. So the RS pin, the EN pin, and then LCD D4, D5, D6, and D7, the data pins. So that'll initialize the LCD, and then that'll give us this LCD object that we can do things with. So we do begin, and then start by telling it how big the LCD is. So we have a 16 character by 2 line LCD. There's a bunch of different commands, and you can look up online how this works, but we'll do LCD set cursor. We'll move the cursor. So 0, 0 will be the top left. And then what I'll do is I'll just print the message that we're going to send. And so that'll just put the message, this message hello world, that'll put that on the LCD. And then on the second line of the screen, I'll just have it print out each bit as it sends it. So go to the second line, and the column will be the bit index. So that'll start at bit 0 and then move, bit 1, 2, 3, 4, 5, 6, 7 across. And then that'll be on the second line, which it starts at 0. So line 0 would be the first line. So now we're on line 1 as the second line. And then we'll print the bit. So TX bit, that's a Boolean. So if it's true, then we'll print a 1. Otherwise, we'll print a 0. So that'll output that bit on the second line. And then what we'll do is after we've output the whole character and we move on to the next byte, I'll clear the second line. So here, clear the second line of the display. So we'll just go to 0, 1. So that's the beginning of the second line, and just print 8 spaces to just write over the zeros and ones that we may have printed there on the previous character. And then the other thing I can do is the LCD has this cursor feature, which will let you put a little underscore cursor on a character. And so what we can do is we can keep track of which byte we're sending by moving the cursor along underneath the character of our message. But basically, every time I print, what I want to do is move my cursor back to the character that we're currently working on. So I'll set the cursor to point to the byte that we're writing on the first line. And then if you just say lcd.cursor, that'll turn the cursor on. And then we probably want to turn the cursor off when we're doing other things. So that's no cursor. Same thing down here. So just copy these. And then when we update the display here, we'll go back and highlight the byte that we're sending. And then same thing here, turn the cursor off before we start. Hopefully this will all make sense once you see it actually working. And then actually one other thing I'll do is at the very end here, I'll just turn off the data bit. Yeah, because you notice now it just sort of ends either on or off depending on what data we happen to be sending. So this will just turn it off when it's done. So let's go ahead and upload this and see if it works. Oh, it looks like I missed a semicolon. Oh, I missed a period. There we go. Now it's programming. And there it goes. Now it looks like it's outputting something. And you can see that cursor moving along, showing which character it's actually outputting. And then you can also see the ones and zeros that are being printed as it outputs each bit. And so this should be easier to keep track of because you can see when it outputs a 0, the LED should be off, and when it outputs a 1, we should see the LED on. So even if you don't have an oscilloscope, if you slow the clock down a bit, it should be fairly straightforward to match this up and just to verify that it's doing what we expect it to do. And then once you verify that it's outputting the right bits, you can also look and see, so this is, what is this value? This is 32 plus 1 is 33. So at least the last byte it outputted was a 33, and 33 is in fact the ASCII value for an exclamation point. So you can also verify that. So the LCD makes it a lot easier to just, both see what's going on as well as troubleshoot this. So great, now that we've built something that will transmit this hello world message using NRZ encoding, let's move on to building a receiver. And so for the receiver, actually the hardware is going to be the same because most of the hardware here is for the LCD, and the receiver is going to have an LCD as well. So, it's going to be hooked up the exact same way. And then the transmit signal, instead of being a transit signal, that we've got a receive signal. But I'm still going to hook it up in the same place. So I'm going to hook it up to D3, but now D3 will just be an input instead of an output. And we'll hook the output of this over to the input here, and that'll be the input now for our receiver. But otherwise, the hardware is going to work the same way. So really the only difference is, I'm using a green LED here just so that once I program them, I can tell which one's which, because they're certainly going to be programmed differently. But other than that, the hardware is going to be the same, so I won't walk through building all of it. But it is going to be programmed completely differently. So let's go ahead and program the receiver. So for the receiver, we're just going to start a new sketch. And we'll start by defining the pins. And actually, we can copy a bunch of that from our transmitter because our pin assignments are going to be pretty much the same because most of them are for the LCD. The only different one is going to be the transmit data is now going to be receive data. So pin 3 is going to be for receive data. And then in our setup, we'll want to set our pin mode for that RX data pin, that receive data pin, to be input. So this is obviously a big difference right now. Our receive data is an input pin rather than over here we had our transmit data, which was an output pin. But then beyond that, we can also copy some of the LCD stuff. So I'll copy the include there for our liquid crystal library. And then the initialization here is also going to be the same. Although I'm going to put it outside the setup here so that we have a global variable because I want to be able to use this LCD variable from inside the setup as well as in the loop because we're actually going to be doing all of our reading in the loop here. But we do need to set up the LCD in our setup. And that's just the LCD 16,2. Tell it that it's a 16 character wide by 2 rows. And then, our receiver also needs to keep track of our message. So we'll define a character string. We'll just say 16 bytes for now. And this will be the message that we're receiving. Although in our setup to start out with, we'll start with that string as empty because we haven't received anything yet. And then in the loop, what we'll do is we'll add characters to that message string as we receive them. So we can have a Boolean, which is our received bit. And that's just going to equal whatever value is on the RX data signal line. So we do a digital read for the RX data pin. That'll tell us what bit is there. But of course, we want to do this at the right time. So we'll put a delay in here of 200 milliseconds because we expect to receive a bit every 200 milliseconds. And so that's pretty much it. We're receiving these bits. Of course, it's not very useful if we don't do something with them and actually display what we're receiving. So what we need to do is we need to take this bit, build a byte from that as we receive bits, add it to our message, and then output all of that to the LCD screen. So what I'll do is I'll define a byte, which is our received byte, and that can start equal to 0. And then I'll also define an integer for our bit position. We'll start that equal to 0 as well. So that tells us which bit we're on, because we're going to be receiving these bits one at a time. And then for every 8 bits, we want to make a byte. So what we'll do is say if the received bit, which basically means if it's a 1, so if it's on, if we read a high value, then what we want to do is we want to take our RX byte and flip the bit corresponding to our current bit position. So what we can do is we can OR it with a value that has the current bit position set. So if we do 0x80, that'll be the first bit, but then we can shift that right to the bit position that we're on. And then, bit position will just go from 0 to 7. So for our first bit, it'll be 0. and this will basically flip on that first bit in the receive byte. And then the next time we come through the loop, what we'll do is increment that bit position. And so the next time through the loop, bit position will be 1. And then it'll shift this 080 to the right. So it'll be 0x40. And then if that bit is set, it'll flip that bit. And then next time through, bit position will be 2, and so on. And it'll flip those bits one at a time. And then what we want to do is if we come in here and if bit position is 8, then we want to set bit position back to 0. Of course, the other thing we want to do once we wrap around is set our byte back to 0, because the way we're building this byte is it starts at 0, and then we just only flip on those bits where the bit is a 1. And so as we receive this byte, if we get to a point where we've received the whole byte, so if we're at bit position 8 here after we've received a bit, so we've received that 8th bit, then what we'll do is we'll concatenate on the byte that we got. So take our message and concatenate on the received byte, and that'll just be one byte that will stick on there. And that ought to basically be it in terms of receiving that message and building it up. But of course, we want to output stuff to the LCD so we can actually see what this is doing. We'll start by going to the top and printing the message. So whatever our message happens to be at this point in time, we'll print that out. And then we'll go to the second line. And then we basically just want to print each bit. So we'll do a for loop here to go through, all 8 bits. And then we want to print that bit. So we'll do lcd.print and then the received byte, but then we want to figure out if the bit is set. So we're going from, bit, 0 through 7 here basically. So we want to check if that's set. So we can AND the byte that we've built up so far by 0x80 shift right I, and that'll tell us if the ith bit in receive byte is set. And then if it is, we want to print a 1, otherwise we'll print a 0. But of course we may not have received the whole byte yet, so we only want to print a 1 or a 0 if we've actually gotten that far through the byte. So if we say if I is less than our current bit position, right? Because if we've only received 4 bits of the byte, we only want to print those 4 bits. Otherwise, we'll just print a space to overwrite anything that might be there. And so that should output, so that should output our message on the first line, and then on the second line, it'll output the 1s and 0s that we've received so far of the current byte. And then I can also set the cursor to show just where we are in the message, although in this case, it'll always be just the last character that we're receiving, but I'll do it anyway on the first line and then turn the cursor on. And then before we do all this mess, I'll turn the cursor off. So that should be everything. So this loop function, that Arduino is automatically going to call that as fast as it can. So we'll delay 200 milliseconds and then receive that bit, use that bit to build up a byte, add that byte to our message, and then just sort of print out where we are. And then it'll just go back to the top of the loop and wait another 200 milliseconds and get the next bit. So let's connect our receiver and program this. So plug that in and upload. And there it goes. And you can see it's just printing zeros, which makes sense, right? Because this is our input and our input is just low. So it's looking at that every 200 milliseconds, and every 200 milliseconds it's low. So it reads in a 0. So we're just getting a bunch of zeros. So now let's hook it up to our transmitter and send it some data and see if we can get it to receive that correctly. And so I basically just want to hook up a wire between the data signal on the transmitter here and the data signal on our receiver. And because our signal is a voltage, and a voltage only makes sense as a difference of potential, both of these need to share the same ground potential. So in practice, what that means is that our transmitter and receiver need to be connected with 2 wires, one for the data signal and then one for the common ground. So let's power these up and see if it works. So I'll just connect a 5-volt power supply to our receiver, and we see it's receiving those zeros. And then I'll connect power to our transmitter. And we can see it's starting to receive some zeros and ones, but the message that we're getting looks to be just gibberish. So what's going on there? Well, of course, what's happening is the transmitter is sending each character as 8 bits, and the receiver is receiving those 8 bits, but the 8 bits aren't necessarily lined up. That is to say, like the 8 bits that make up the H here that we sent, some of those bits might have been received, partway through a byte here. And so those bits got shifted over. And so this first byte, which is this weird little character here, might have just been some of the bits at the end of the H. And then the next character, which looks like a blank, might have been, the rest of the bits from the H, and then some of the bits from the E, and so forth. And so if it doesn't line up, obviously we're not going to receive the same thing. So what we can do is try to get these things in sync. We can reset both of them at the same time. And let's see if we can get it to be synced up. Well, there's the H, so it looks like we're doing okay there. And now it looks like it's working. But what happened here? It looks like we were receiving things just fine, but then it looks like something went off the rails. So what's going on there? Well, if we look back at the code, there is something that might be a problem, which is when we're transmitting. Let's see, here we are transmitting. We've got this for loop, and we're just going through each bit, and we're writing and updating the LCD, and then delaying. This is going to be 200 milliseconds. When we're reading, we're delaying 200 milliseconds, and then we're reading the bit. And then we're also updating the LCD, but we're actually doing a little bit more processing here. We have this for loop. We're printing a little bit more here, and we're also moving the cursor, and we're printing the whole binary. Whereas here, we're only printing one bit. We're moving the cursor, we're printing one bit, and then we're moving the cursor back. But we're doing less here when we transmit. And so even though our delay statement is the same, this is going to be 200 milliseconds, and then our delay statement when we receive is 200 milliseconds, there's some extra delay in our receiver because we're doing a little bit of extra processing. So if we reduce this delay, instead of 200, let's make that like 198 maybe. So let's give that a try. I'll reprogram the receiver. So I'll plug in USB here and hit upload. And there we go. So now we've got the slightly slower speed here. So maybe this will be better in sync. So let's reset both of them and give it a try. So far, so good. And looks like that's not quite enough. I don't know if I'm too slow or too fast. Let's try 196. Upload that. Okay, now let's reset both of these and see if that's better. Well, this certainly looks a lot better. This is a lot more promising, right? Oh, but almost. What happened here? So this last character, instead of an exclamation point, we got a quote. We almost made it to the end. So what's going on here? And the reality is actually this delay thing is really a bad way to try to synchronize these things because we really don't know how much time this processing is going to take. So we could tweak this and maybe get a little bit better and get a little bit longer message, but this is hardly what I would call a reliable means of communication here, because this is only going to work for a little bit while these things stay in sync, but eventually they're going to get out of sync. So delay really isn't the right way to ensure that we're reading at a fixed time interval. Now there are better ways with Arduino to do that. So one would be using timer interrupts. And with timer interrupts, we could have the Arduinos run code exactly every 200 milliseconds. So we could have the transmitter transmit a bit exactly every 200 milliseconds, and we could have the receiver read input exactly every 200 milliseconds. And when I say exactly every 200 milliseconds, I mean as exact as the Arduino can possibly get using the clock oscillator that's on the Arduino, which is this little ceramic resonator, which is this little thing here that's going to oscillate at 16 megahertz. So how accurate is the clock oscillator on the Arduino? Because that's going to tell us the best case we can possibly do in terms of getting the timing synchronized between both of these. We can actually take a look at that by hooking our oscilloscope probe up to it. And then if we look at the oscilloscope, we can see, well, here's our 16 megahertz clock. Looks pretty good, but let's actually measure to see how close it is to 16 megahertz. So we've got a frequency counter here. We can turn that on to channel 1. And it looks like it's 15.979 megahertz, so not exactly 16 megahertz. And I wouldn't expect it to be exactly 16 megahertz because these ceramic resonators that are on these Arduino Nanos aren't the most precise clock source in the world. But the real question is, how different is the clock on the receiver here from the clock on the transmitter? So let's hook up another probe to the clock on the transmitter just to compare. And so now that's hooked up. Let's turn on channel 2 and compare. It's already, we can see we're getting something here, but it's not in sync with channel 1, which I wouldn't expect. There's no reason to expect these clocks to be in sync. We can change our trigger here. So if we trigger on channel 2, we can have channel 2 in sync, and then channel 1 goes out of sync. So that suggests that they are different frequencies. But let's actually measure and see how different they are. So we go back to our measurement frequency counter here. So channel 1 was 15.979 megahertz, and channel 2 is 16.03 003 megahertz. So they are different. But how big a difference is that, and does it matter for what we're trying to do in terms of transmitting data from one to the other? Well, if you look at the difference here, it's about 0.15%. So how big a deal is 0.15%? Well, 0.15%, another way to look at that, if you take 1 over 0.15%, you get about 667. So what does that mean? So that means if the transmitter is the faster one, which it is, then for every 667 bits that the transmitter sends, the receiver is only going to try to receive 666 bits. So that means we're going to get out of sync in under 666 bits. So that's obviously no good. So it looks like, unfortunately, we're out of luck if we want to use this NRZ encoding just by itself. Maybe better clocks would help a little bit, but they're only going to get you so far. And actually, as the bit rate is faster, as we send more data faster, then the importance of having those clocks synchronized becomes even more important, because the shorter the time interval between the bits, the more important it is for both sides of this communication to agree on how long that interval is. So trying to improve the clocks is kind of a dead end unless you go for atomic clocks or something, completely unreasonable. But what is very easy and very common is to send the data like this, but then also send a clock. So essentially, we'd send two signals that would look something like this. We'd have the data, which looks just like our NRZ encoding. In fact, it's exactly the same. But then we have a second signal that we would send, which would have a clock. And then the clock would just pulse on and off. And then the other receiver could then use that clock to figure out when to read the data. And so then it doesn't matter if the internal oscillator, if those are off by a little bit, because if the transmitter is sending its own clock along with the data, then you can just recover that clock and read the data using that clock. And this is actually pretty easy to implement. The only downside is that instead of having one data signal and then of course the ground, we'll have two data signals, or well, a data signal and a clock, but two signals plus the ground. So it does take a few more wires to transmit this way, but for our little setup here, that's just fine. So for clock signal, that's just going to be another pin coming off our Arduino here. So let's see, if we're using pin 3 for our data, then we're using pin 4, 5, 6, 7, 8 for the LCD. And let's use pin 2 for the clock. And I'll just hook that up to another LED over here, because this is just going to be a second signal that we're going to send across from our transmitter to our receiver. And just like before, I'll connect that LED to ground through a current limiting resistor. Again, that's a 330 ohm resistor. And same thing here on the receiver. I'll connect pin 2 in the same way to an LED down here. And finally, instead of just these two wires connecting data and ground, we're going to need 3 wires connecting clock, data, and ground. So I'll hook up clock, data, and ground on our transmitter. And then the other end here, I'll connect clock, data, and ground on our receiver. And so there we go. Now we have our new clock signal. And then of course a new connection between the transmitter and receiver, because we now need a 3rd wire for our clock. So now let's go ahead and program. So now to add the code to send the clock, we'll start with the transmitter. We've got another pin assignment here. Transmit clock is on pin 2. We'll want to set that to an output pin. So pin 2 will be an output pin on our transmitter. And then when we transmit here, we're outputting our data bit. And then we basically want to then pulse our clock. So output the clock high and then low. So once our bit is set on the data line, then our clock goes high and then low to signal that we've got a new bit there. But I am going to tweak the timing a little bit here. So what I want to do is, instead of having our whole delay down here at the end, what I'll do is I'll put a delay right after we set the bit, and I will delay for half of our delay time then. Then I'll update the LCD, then I'll pulse the clock, and then actually while we're pulsing the clock will go high for the other half of our delay, and then go low. So what we've got here is we're transmitting our data byte, or bit rather, one bit at a time here. We're transmitting our data bit, and then we're delaying for half of our bit time, then updating the LCD to say that we're sending the bit. And we do that right before we actually pulse the clock high, which is kind of the moment that the bit is being sent, if you will. We pulse the clock high, then wait for the other half of the bit time, and then the clock goes low. So that'll be the transmitter. Let's upload that and give that a try. And there it goes. And we can see it looks like it's transmitting hello world, and now we can obviously see the clock is flashing. And so every time this flashes, that indicates that we're sending a bit. And just so we're clear what that looks like, we can hook the scope up to that as well. So hook one probe up to our clock line, and then hook the other up to our data line. So with the scope hooked up, we can see both of them are currently 0. But if we reset, actually what I'll do is I'll single shot this, and then reset. So it starts transmitting again. And there we go, we're capturing. And you can see the clock on the top and then the data on the bottom. If we take a closer look, there's a couple things I'll point out. First, it's easy to pick out each bit of data just by looking at the points where the clock goes from low to high. The receiver doesn't necessarily need to know anything about the expected timing. In fact, the other thing I'll point out is that while the clock looks pretty good on the left here, where it's lined up with these 500 millisecond grid lines, there's enough of a skew that we get over to the right side here, and you can see the clock doesn't even line up with those 500 millisecond grid lines anymore. So we're definitely not doing a great job of hitting our target rate of 5 bits per second, but that's okay. We're sending our less than perfect clock, and it's the rising edges of that clock that matter. And as long as the data bits always line up with the clock, then it's okay if the clock drifts a little bit. And this is a really important aspect of engineering, to design systems that can deal with things going wrong or deal with imperfections like this. So in this case, it's timing, and because our clock doesn't have to be perfect, we can get away with cheaper, less accurate timing hardware. But of course, at this point, we're still not using the clock for receiving, so we still may get some of these errors like this if we're not perfectly synced up. So let's take a look at what we can do about that. So if we come over to the receiver here, currently we've got this loop where we're delaying, approximately the right amount of time between bits and then reading the bit. But what we want to do is we want to read the bit when the clock transitions high. And there's actually a really cool way to do that with the Arduino, which is using interrupts. So the Arduino supports these pin interrupts. And basically the way that it works is you define a function that you want to have called when a pin transitions. So we can make a function called onClockPulse. And then what we can do is in the setup here, we can attach an interrupt. And the way this works is you have to pass in the interrupt number, which you can get using this digital pin to interrupt function. And then you pass the pin number. That'll give us the interrupt number that we want to attach. And then you give it the function name that you want it to call. So if we say onClockPulse, then that's going to call this onClockPulse function when something happens with our receive clock. And then we just need to tell it what we're interested in. So in this case, we can say rising, and that means when the receive clock signal rises, that is, it goes from 0 to 1, then call this function. And then of course in this function, that's when we read our bit. So basically we can take all of this stuff, well, maybe not the LCD stuff, but we can take all of this stuff where we read that bit and move it into this onClockPulse function. So basically this says, essentially we won't do anything in our loop. We can get rid of this delay, I suppose. We won't really do anything in our loop, maybe still update the LCD there, but we won't read any data in the loop. What we'll do is we'll only read data in this onClockPulse function, and that function's only going to get called when the clock pulses. So in this onClockPulse function, we'll do all this stuff we were doing before. So we'll read our RX bit, our received bit. We'll update our bit position if we're at the end of a byte. Otherwise, we'll update our byte and increment our bit position. And then if we've gotten to the end of the byte, then we'll update our message and add the new byte to it. So then what do we want to do in the loop? Well, I guess we still want to update the LCD, but we don't want to just update it constantly. So what I can do is create a variable. We'll call it LCD, update.lcd, and start off as true. And then in the loop, we can say if update LCD is true, then update the LCD. So basically in our loop, we're only going to do anything if this update LCD thing is true. And if it is, then we'll update the LCD. But first thing we'll do is set that to false. So if update LCD is true, then we'll set it to false and then update the LCD. And then at that point, our loop isn't going to do anything. And then we want to change this to true when we receive a bit. So here in our onClockPulse, when we get that clock pulse, we'll receive the bit, we'll update our bit position, we'll update our message, we'll update our receive byte, and then we'll say update LCD equals true. And then the next time through the loop, it'll update the LCD. We don't want to actually update the LCD in this clock pulse because this is an interrupt handler. And in an interrupt handler, you want to keep it pretty tight. You don't want to waste a bunch of time in the interrupt handler. But also the LCD library might actually make use of interrupts. And so if we're calling it from inside an interrupt handler, then interrupts will be disabled and it may not work. So it's best to not do very much inside an interrupt handler. Just sort of update your data structures and then set some flag that we can then use in our loop. One other little gotcha with interrupt handlers is any of the variables that we're modifying in the interrupt handler. I'll set this volatile keyword on here. And that basically just tells the compiler, don't try to do too much optimization with these things because there's an interrupt handler that might be mucking around with them when you don't suspect, because the compiler doesn't know exactly when this interrupt handler might get called because we don't really know until the hardware actually calls it. So anyway, that should do it. So let me connect the USB to the receiver there and upload this code. RX clock's not declared. Oh, thought I defined that. Guess not. And there it goes. And so there we go. And the first thing you'll notice is that we're not receiving those zeros anymore. So remember before, every 200 milliseconds, it would look at the data signal. And if it was low, it would say, well, must be receiving a zero. And it would just, receive a zero every 200 milliseconds. But now it's actually waiting for that clock. So we don't see it just printing those zeros like it was before. The other nice thing about that is that it's also not only waiting for the clock to receive a bit, it's waiting for the clock to receive the first bit. And so we don't have to worry about keeping them in sync by resetting both of them at exactly the same time. So it's already just waiting for that first bit of the first byte. So if we just reset the transmitter, then as soon as it starts sending, it starts receiving a byte, and the byte is always going to be aligned just perfectly. And so now we see we're receiving the message just fine, and in fact, we should continue to receive the message just fine. I wouldn't expect any problems now that we have the clock in there to keep everything in sync. And so we can continue. We can just reset this and reset the transmitter whenever we're ready and retransmit that signal. And we should be able to do this all day. We should have no problems transmitting this because we've got the clock. We'll keep everything in sync. It doesn't matter if the timing is a little bit off. We really should have no problems with this at all. However, there are still things that could go wrong. So it's always possible that an error introduces itself into the transmission. And that's the case anytime that you have any kind of communication network. There's always a chance for errors to crop up. But what happened here? Well, I did something a little bit sneaky. The connection between the transmitter and receiver, I have this little button in here that I can push that interrupts the data signal. And so I can actually cause it to miss bits by pushing this. And so I had that off frame and just introduced a little bit of a bit error right there in the middle of the message. And you might think, well, that's not very realistic. I mean, how often are you sending a message where someone has a way to interrupt the message while you're sending it? But the reality is any communication system is susceptible to errors. And in fact, any communication channel has a theoretical maximum bandwidth, and particularly as the bit rate gets close to that theoretical maximum, then the channel becomes more susceptible to noise. And noise can cause errors like that, where you miss a bit or something is off a little bit. And so I put this switch here. Obviously, when we're sending 5 bits per second over just a short distance, we're not anywhere near close to the theoretical maximum here. But I put this switch here to simulate that because, in high-speed or wireless networks, things like that, it's very common to get errors. And what I want to talk about in the next video is how do you detect those errors? Because what happened here is the transmitter sent a series of bits, and the receiver actually received a different series of bits. And, you can look at this and say, well, that's probably not the message that we intended to send. But as the receiver, how do you know that? This is certainly a representation of the bits that the receiver received. It just happens that I interrupted some of those bits, and so we got a bit of a weird message. But is there a way to tell with, some amount of certainty on the receiver side here that, yeah, we got these bits, but the bits were wrong? Well, it turns out there are a number of different ways of detecting that and figuring that out and knowing that maybe you need to ask the transmitter to retransmit the message or even knowing how to reconstruct the correct message with incomplete data. And so that's what I'll be covering in the next video. So this video was really just kind of a lab setup, I guess, where we're just setting this up, particularly with this ability to introduce these errors so that we can explore a little bit deeper in the next video how to detect those errors and perhaps even how to correct them in future videos. I want to thank my supporters on Patreon who are helping make more of these videos possible. I particularly appreciated their feedback on this video. Specifically, I asked them if I was hitting the right balance between taking the time to walk through every step of the process while keeping it engaging. The overwhelming feedback was very positive, but I'd love more feedback if you've got a different perspective. And if you'd like, consider supporting me on Patreon if you're able. If not, that's totally cool. I know there are a number of people who support this work explicitly to make sure that it's free for others who aren't able to support it directly. So definitely an extra thank you to them.